Okay, so we will now address what we found on our solutions for the Schrodinger equation for infinite quantum wells. First of all, we have the n, which n in this case represents the length of the Hamiltonian matrices. So if n is equal to 1000, then it will be a 1000 by 1000 matrix. First, we plug on all the values that we will use, which in this case is a, which is the width of the quantum well in nanometers, and all the other masses and the constants and electrovolts to joules. Then we create the diagonals, which this is the main diagonal, which is multiplied by the factor, which in this case is h squared divided by the mass times x squared, which is the delta x. Then the off diagonals, which are the ones on the side, because the Hamilton matrix is divided on three diagonals, and all the other spaces are filled with zeros. And then we have the H diagonal, which is the one that we plug on all the diagonals inside. And then we say that the first and second column are zero. And then we look for the eigenvalues with this equation. Then we sort them and we divide it by the electrovolts to create the four energy levels in this case that we are going to evaluate. And then we create a visual representation of the quantum well with the energy levels on where they will be and the width of each one of them. So first we will address the questions, which are what happens if we change the n. So first of all, we have a smaller n, and we can see that the energy levels are bigger in this case by just some decimals, but they are bigger. And if we plug a bigger value, we will wait. But for now, we are going to raise the next question, which is what happens if we change the mass. Let's say it is not made of the materials that we used. So let's say now it has a mass of 0.099. And now the energy levels are a ton smaller, which means that with a bigger mass, the values would be smaller. So now we can check on here that it has ended, and also the decimals. By decimals, it is smaller, which means a bigger n means smaller energy levels. Then we have the almost the end of this, which we have the theoretical levels, which are plugged in this equation. We have the values that we said before, and then the n represents the energy level that we are trying to look for. So we are trying first to look for the first energy level, and we have this theoretical energy level that we can compare to the other ones to see what the standard the error is over here. The smaller the error, the better the representation, the computation is made. And at last, we have what happens if we change the width of the quantum well, which in this case, we are going to see a 15 nanometers width. So we can see that when we change it and we keep everything else almost the same, we can see that the energy levels also decrease. So we can see that for a bigger A, the energy levels will decrease. If we compare it to the first one, where we have the same N, we only change the A, the energy levels are decreased by a mile. And also, we can see that the weight is also bigger in the presentation. And at last, we can evaluate what happens if we change this to a 5. So we may see that this will become smaller and the values will become almost nothing. So it's a big factor of the way this works. And at last, we need to evaluate the orthogonalization of the wave function, which in this case are the vectors. We use the function to the vectors, and we know that the dot product equals to 0. They are orthogonalized, if else it doesn't work. And in this case, it works, so they are orthogonalized, which means that this is an important equation to the theoretical way that our world is ruled.